And for decades, nutritional advice told us the same thing. If you want to lose fat, stop eating fat. Low-fat yogurt, low-fat cereal, low-fat everything. And yet rates of obesity, type 2 diabetes, and metabolic syndrome have never been higher. So what went wrong? Here is what the science actually says. Dietary fat is not the primary driver of body fat accumulation. The process that fills your fat cells, the biological emergency that determines whether you store energy or burn it, begins within 30 minutes of eating the wrong kind of carbohydrates. Today, I'm going to walk you through that process minute by minute, step by step, using the same molecular biology your own body is running right now. I'm a physician, and the pathway I'm about to describe is one of the most important and least explained processes in modern metabolic medicine. Stay with me for 10 minutes. It could change how you eat for the rest of your life. The moment refined carbohydrates, white bread, white rice, crackers, pastries, sugary drinks enter your mouth, digestion begins immediately. Salivary amylase starts breaking starch chains into maltose and glucose fragments before the food even reaches your stomach. Compare this to what happens with whole foods. When you eat brown rice or a whole apple, the intact fiber matrix, the natural cell walls of the grain or fruit, physically slows that breakdown. It's like trying to dissolve a sugar cube versus dissolving loose sugar granules. The total amount of glucose may be the same, but the delivery speed is completely different. In refined carbohydrates, industrial milling has already destroyed that protective structure. The food has essentially been pre-digested. By the time it reaches your small intestine, roughly 3 to 5 minutes after swallowing, glucose is already flooding into your bloodstream. Within 5 to 15 minutes, blood sugar begins rising rapidly. In some individuals, blood sugar can climb to 140 or even 180 milligrams per deciliter after a high refined carbohydrate meal. Clinically, this is called post-meal hyperglycemia. Your pancreas detects this glucose surge through specialized beta cells that function as biological glucose sensors. Within minutes, those cells release insulin. Insulin acts as the master traffic controller of metabolism. Its job is simple but critical. Remove excess glucose from the bloodstream and move it into cells. It does this by activating proteins called GLUT4 transporters on muscle and fat cells. These transporters act like doors, allowing glucose to enter the cell. When this system is working properly, it's remarkable. But the problem appears when glucose enters the bloodstream faster than the body can use it. And that is exactly what refined carbohydrates do. As insulin rises, the body first attempts to store glucose as glycogen. Glycogen is the body's short-term carbohydrate storage system. The liver can store about 100 grams of glycogen. Your muscles can store roughly 400 to 500 grams. But for many people eating modern diets, these storage tanks are already partly full from previous meals. Think of it like arriving at a gas station with a fuel tank that is already 70% full. There's only so much additional space available. When glycogen capacity is exceeded, the body activates an entirely different metabolic pathway. Excess glucose must now be converted into fat. This process is called de novo lipogenesis, which literally means the new creation of fat. Inside liver cells, excess glucose is converted into a molecule called acetyl-CoA. An enzyme called acetyl-CoA carboxylase B converts this into malonyl-CoA. Then another enzyme complex called fatty acid synthase links these carbon units together, building long fatty acid chains. One of the primary products is palmitate, a 16-carbon saturated fatty acid. In simple terms, dietary carbohydrates have just been converted into body fat. Two molecular signals trigger this process. The first is insulin, which activates a transcription factor called SREBP1C. The second is glucose itself, which activates another factor called CHR-EBP. When both signals are present at the same time, they amplify each other, dramatically increasing fat production inside the liver. The newly created fatty acids are packaged into particles called VLDL, or very low-density lipoproteins. These particles carry triglycerides through the bloodstream. They eventually arrive at adipose tissue, your fat storage depots. At the walls of blood vessels supplying adipose tissue, an enzyme called lipoprotein lipase breaks down these triglycerides into free fatty acids. Those fatty acids are absorbed into fat cells called adipocytes, where they are reassembled and stored. As more fat accumulates, the fat cell enlarges. This process can occur in two main storage locations. Subcutaneous fat sits just beneath the skin. Visceral fat, however, accumulates deep inside the abdomen around organs such as the liver, pancreas, and intestines. Visceral fat is metabolically active and significantly more dangerous. It releases inflammatory molecules, disrupts hormonal signaling, and is strongly linked to type 2 diabetes, cardiovascular disease, and premature mortality. As fat cells enlarge, they begin secreting a hormone called leptin. Leptin functions as a long-range fullness signal. It travels to the hypothalamus in the brain and tells the body that energy stores are sufficient. In a healthy metabolic system, this signal helps regulate appetite and maintain balance. You eat, energy is stored, leptin signals fullness, appetite decreases. But problems arise when fat storage happens repeatedly. If fat cells remain chronically overfilled, leptin levels stay elevated for long periods. Just as chronic insulin elevation can lead to insulin resistance, chronically high leptin levels can lead to leptin resistance. In leptin resistance, the brain stops responding properly to the signal. Even when the body has abundant energy stored as fat, the brain perceives a state of energy shortage. The result is increased hunger, reduced motivation to move, slower metabolism, and a powerful drive to keep eating. This is not simply a failure of willpower. It is a breakdown in biological signaling. When we step back, the entire process becomes clear. A refined carbohydrate meal triggers a rapid glucose surge. Insulin rises sharply. Glycogen storage reaches capacity. The liver converts excess glucose into fatty acids through de novo lipogenesis. Those fats are packaged into VLDL particles and transported through the bloodstream. Lipoprotein lipase extracts the fats and stores them in adipose tissue. Fat cells enlarge. Leptin levels rise. Over time, leptin resistance develops, which drives hunger and continued energy intake. This cycle can repeat multiple times per day in diets dominated by refined grains, sugar, and ultra-processed foods. Fortunately, there are simple strategies that can interrupt this process. First, choose intact grains instead of refined grains. The natural fiber structure of whole grains slows glucose absorption and reduces the magnitude of the insulin spike. Second, adjust meal sequence. Eating protein and fiber before carbohydrates can significantly reduce the peak rise in blood glucose after a meal. Third, move after eating. A 10 to 15-minute walk shortly after a carbohydrate-containing meal activates glucose uptake in muscle through pathways that do not require insulin. This allows muscles to absorb glucose directly and reduces the metabolic load on the pancreas. Your body is not malfunctioning. It is responding exactly as it was designed to respond to the signals it receives. When we change those signals, we change the outcome. If this explanation changed the way you think about what's happening inside your body after a meal, consider subscribing for more science-based breakdowns of how human metabolism really works. I'll see you in the next video.